Have you ever stopped to think that a fundamental rule of the universe, a rule that's all about uncertainty, is the very reason you and I can even exist? Well, that's the Heisenberg Uncertainty Principle in a nutshell. It's not just some weird footnote in a physics textbook, it's the law that holds atoms together. Okay, let's dive in and really figure out what this thing is all about.
So you've probably heard an explanation that sounds something like this one, right? It's the classic high-speed camera analogy. You snap this perfectly crisp photo of a tennis ball. Boom, you know its position down to the millimeter. But because it's a frozen moment in time, you have zero clue about its momentum. A blurry photo would be the opposite. You'd get a sense of its momentum, but its location would be a smear. It's simple, it's intuitive, and it's completely wrong.
So is that really all there is to it? Is one of the deepest, most fundamental principles of reality just a matter of picking the right camera setting? The short answer is a big, fat no. That simple explanation doesn't just miss the point, it completely hides the mind-blowing truth of what's actually going on.
To really truly wrap our heads around the uncertainty principle, we first have to unlearn all the common explanations that get it wrong. We've got to move beyond these flawed analogies and start fresh.
Okay, let's break down why these easy explanations just don't hold water. The whole camera problem? Come on, just use a video camera. Look at the very next frame and you can calculate the velocity. That's a limitation of our tools, not a law of nature. Then you've got the other classic, the idea that to see an electron you have to bounce light off it, and that little collision knocks it around, messing up its momentum. But again, that's not it. The uncertainty principle is way, way more fundamental. It's a property of the universe that exists even when nobody is looking. So to get this right, we have to go all the way back to the beginning. We need to completely rebuild our understanding of what a quantum thing, like an electron, actually is. So just for a minute, forget everything you think you know about waves and particles. You know, the legendary physicist Richard Feynman gave us the absolute perfect way to think about this. He said, imagine you found a new creature. It flies like a pigeon, but it has the fur and face of a mouse. You wouldn't say it's both a pigeon and a mouse, would you? Of course not. You'd say it's a completely new kind of animal that just happens to share some properties with them. And that, right there, is the quantum world.
I mean, think about what we're used to in our everyday world. You've got classical particles, like little grains of sand. They come in countable lumps, and you find them in one specific spot. And then you have classical waves, like ripples on a pond. They're spread out, continuous, and they exist in many places at once. They seem like total opposites.
And this brings us to the crucial point. An electron is a quantum object. It's its own screwy thing, just like Feynman said. It has a particle-like quality. You always find it as one whole lump. You never find half an electron. But it also has a wave-like quality. The probability of where you might find that lump is spread out and behaves exactly like a wave. It's not a particle, it's not a wave, it's something totally new that has features of both.
Okay, so if these things are part particle and part wave, how do those two sides of their personality talk to each other? Well, the answer to that question is the key that unlocks this entire mystery. The story kicks off in the early 1900s. Planck and Einstein figured out that light, which everyone thought was a pure wave, actually comes in these little packets of energy called photons. Then, in 1924, this physicist named Louis de Broglie had an absolute stroke of genius. He realized that if a photon's energy is tied to its frequency, and frequency is tied to wavelength, then a photon's momentum must be tied to its wavelength. And then he made this huge leap of faith. What if this isn't just true for light? What if it's true for everything, including electrons? And guess what? He was totally right. This is the de Broglie relation. And it is one of the most important equations in all of quantum mechanics. It says that the momentum of any quantum object, that's its particle-like property, is directly connected to its wavelength, its wave-like property. And here's the kicker, they're inversely proportional. A really short, tight wavelength means really high momentum. A long, stretched-out wavelength means low momentum. They're locked together.
All right, we've got all the pieces now. We know that quantum objects are wave-like, and we know how their wavelength is locked to their momentum. With just these two ideas, we can actually build the Heisenberg Uncertainty Principle from scratch, right here, right now.
So let's do a little thought experiment together. Let's imagine an electron, and we know its momentum perfectly. I mean, zero uncertainty. What would its wave-like side have to look like?
Well, if we follow de Broglie's equation, a single precise momentum demands a single precise wavelength. And logically, the only way you can have a wave with one perfect, unchanging wavelength is if that wave is a perfect sine wave that just goes on forever and ever across the entire universe. Any little change or break in that wave would mean you're introducing other wavelengths into the mix.
And here is the first really mind-bending result. For this electron, the uncertainty in its momentum is 0. We know it exactly. But what about its position? Remember, the probability of finding the electron is tied to the wave. And since this wave stretches across the entire cosmos with the same height everywhere, the probability of finding that electron is the same everywhere. Its position uncertainty is infinite.
So how do we make this more realistic? How do we actually find the electron somewhere? Simple. We add more waves. If you add a second wave with just a slightly different wavelength to our first one, they start to interfere. In some places they add up, and in most other places they cancel each other out. And what you get is a little bundle, a wave packet, a localized area where there's a high probability of finding the electron. But look at what we've done. We had to add a second wave, which means our object now has 2 possible wavelengths, and therefore 2 possible momenta. Its momentum is now uncertain. And that, right there, is the entire principle. To make the position of a quantum object more certain, to squeeze that wave packet down to a smaller size, you have absolutely no choice but to add more and more waves with different wavelengths. And every single wave you add increases the range of possible momenta. It's a fundamental trade-off that's baked into the very wave nature of reality. It has nothing to do with us measuring it. It just is.
Now, this might all seem like a pretty abstract mathematical game, but this principle has probably the most profound consequence you can possibly imagine. It explains why the atoms that make up you, me, and this entire planet don't just instantly collapse. See, according to 19th century physics, there was a huge problem. An electron orbiting a nucleus should be constantly giving off energy, and that should cause it to lose speed and spiral down into the nucleus in a fraction of a second. Based on everything they knew, atoms shouldn't be stable. So why are they?
The uncertainty principle is the hero of the story. An electron isn't a tiny ball, right? It's a quantum object. It's a wave packet. Now, if that electron started to fall towards the nucleus, its position would get more and more certain. It'd be squeezed into a tiny, tiny space. But what happens when you shrink position uncertainty? You force the momentum uncertainty to get enormous. The electron would get such a huge, unpredictable kick of velocity that it would be propelled right back out, preventing it from ever getting trapped in the nucleus.
And that's really the ultimate takeaway here. This isn't just some strange feature of the quantum world, it is the structural support beam of reality. That inherent fuzziness, that fundamental trade-off between knowing where something is and where it's going, is what props up the atom, stops it from collapsing, and allows for the existence of matter, stars, planets, and us. So the next time you think about uncertainty, don't think of it as a limitation. Think of it as the fundamental reason you're here to think at all.